lecture is about the most important fluid property which will be useful in all the topics of the fluid mechanics, and that is actually as written, that is viscosity. सबसे पहले यहाँ पर बात करते हैं विस्कोसिटी क्या होती है, फिर देखेंगे कि विस्कोसिटी को कौन कौन से फैक्टर्स अफेक्ट करते हैं और कैसे विस्कोसिटी वेरी करती है फॉर द डिफरेंट टाइप ऑफ फ्लूइड्स। तो यहाँ पर सबसे पहले अगर बात करें कोई भी पर्टिकुलर फ्लूइड में, जैसे कि हमने इसके पहले बात करी थी दैट अ पर्टिकुलर फ्लूइड हैव अ प्रॉपर्टी ऑफ फ्लो, एंड अगर मान लिया आपने इस पर्टिकुलर पार्टिकल पे फोर्स लगाया है इन द डायरेक्शन एंड द फोर्स इज कैपिटल एफ, देन पक्की बात है कि इफ देयर इज नो रेजिस्टेंस इन द मूवमेंट ऑफ दीज टू सॉलिड्स देन ओनली दिस पार्टिकल विल मूव, but if there are more particles in between these two particles, then you can say that there is a resistance from the surrounding particles in the movement of the given particle. And if there is a resistance and this particle is moving with a particular speed, let that be u plus du, then the particle which is in the lower layer will move with a smaller velocity. Suppose this particle is moving with a high velocity of this particular magnitude, then the particle in the lower layer will move with a smaller velocity, and there will be a velocity gradient in the direction perpendicular to the force applied. So if you are studying that the velocity of the particle on which force is applied is u plus du, let we can suppose that the velocity of this particle will be u, and suppose if the distance between these two particles in the transverse direction of the force applied is dy, then you can say that among these two particles there is a angle of shear deformation, and this angle of shear deformation, let this be theta. Now suppose the first particle traveled a distance of u into dt in the given time, then the above particle will travel a distance of u plus du into dt distance. If we elaborate this particular equation, you can say that it will be equals to u into dt plus du into dt, and already u into dt is written here. That means this particular distance, that was the extra distance traveled by the above particle, will be equals to du into dt. Writing down the tan theta, you can say that it will be perpendicular upon base. Perpendicular is du by dt and base is nothing but that is dy. So you can say that this tan theta will be equals to du by dy into dt. Suppose the value of this theta is very small, and that is d theta. So you can say that the tan theta will become tan d theta, and that will be equals to du by dy into dt. If the value of d theta is very small, you can say that the value of tan d theta will be approximately equals to d theta. That means d theta will be equals to du by dy into dt. Moving this dt here, you can say that d theta by dt will be equals to du by dy. That means now you can say that the rate of shear deformation, as theta is the angle of shear deformation, you can say that d theta by dt is nothing but that is the rate of shear deformation will be equals to the difference in velocity to the difference in the distance between those two particles. That means you can say that d theta is nothing but that is the rate of shear deformation, whereas the second term, that was du by dy, is nothing but that is the change in velocity with respect to the location. You can say that du by dy is nothing but that is the velocity gradient. As the velocity is changing in this particular fluid particles, you can say that this is telling us about the rate of change of velocity with respect to the position. So you can say that according to this particular equation, that the rate of change of shear deformation will be equals to the velocity gradient in any particular fluid. Now, as we can say that there is a velocity gradient, then it is very sure that there is a resistance to flow, because of which the lower particles are also moving along with the above particle, and that particular resistance to the flow is known as viscosity. So writing down here the definition of viscosity, we can say that viscosity is nothing but that is actually the resistance offered by a fluid particle or layer in the motion of its adjacent layers. देखिए, जैसे यहाँ पर मैंने बोला कि विस्कोसिटी एक रेजिस्टेंस है जो कि एक लेयर पर दूसरी लेयर के कारण लगता है। सो ये भी श्योर है कि विस्कोसिटी कुछ और नहीं बल्कि एक्चुअली एक फ्रिक्शन की तरह ही फोर्स एक्ट कर रहा होगा ऑन द फ्लूइड पार्टिकल्स। सो अगर मान ली ये एक पर्टिकुलर लेयर है ऑफ द पर्टिकुलर फ्लूइड, देन पक्की बात है कि अगर ये लेयर इस डायरेक्शन में मूव कर रही होगी, देन द रेजिस्टेंस अप्लाइड बाय द सराउंडिंग पर्टिकुलर layers will be in the opposite direction. That means the resistance will be in this particular direction, and this particular force is because of the property of fluid that is known as viscosity. Due to this resistance, there will be a change in velocity of the different particular layers, and that is actually resulting into the velocity gradient as we saw in the previous diagram. Now moving ahead to the basic concept of the viscosity, asking you the question that why this viscosity is actually arising in a particular fluid. So the answer will be that there will be a resistance to flow, and the basic reason behind this resistance can be either the force of attraction between those two particles, and hence you can say that viscosity is due to the force of attraction, and this force of attraction is known as it is acting between the particles of the same fluid. You can say that this force of attraction is nothing but that is cohesion. So this cohesion is the basic reason of viscosity in the fluids in which the force of attraction is significant. So among the fluids, you can classify fluids into two categories, that are the liquids and gases, and among these two, liquids have some greater force of attraction. Hence you can say that the basic reason of viscosity in liquids is cohesion. But as we can see that the particles of gases are absolutely free from each other, the force of attraction is almost negligible. Hence you can say that this cohesion will be negligible in gases. So this will not be the basic reason for the viscosity for gases. Then what happens in gases? Why there is some resistance to the flow in gases, or whether there is a resistance or not? So the answer is yes, of course there is a resistance to flow in gases also, but that resistance is due to the collision of particles. So the basic reason of viscosity in gases is collision of particles, whereas in the liquids you can say that there is almost negligible collision of particles in liquids. So you can say that this collision is basic reason in gases, not in liquids, whereas cohesion is almost negligible for the gases. So I hope you all got clear concept about the basic reason of the viscosity. Now moving ahead to the viscosity, related to this viscosity, there is a law that was actually defined by the Newton. So moving to the next portion, that is the Newton's law of viscosity. First of all, writing down the basic statement of this particular law, you can say that this particular statement says that the viscous shear resistance of viscous shear stress between any two layers, acting between any two layers of a fluid, two layers of a fluid is directly proportional to, is directly proportional to the velocity gradient of those two particles, of those two layers. Suppose if you are studying about two layers of a fluid, let this is the layer number 1, this is the layer number 2, and there is a particular distance between those two layers as dy. If the difference in velocities of those two layers is more, you can say that the viscosity or the resistance to flow is also more. That was actually the statement of Newton's law. So you can say that more is the resistance, that means that is actually the resisting stress. So the basic concept in the mathematical term, you can say that the shear resistance acting between those two layers will be directly proportional to the velocity gradient of those two layers. Velocity gradient is nothing but that is the du by dy. If you remove this proportionality sign, then the new constant for the given particular fluid will be introduced, and that particular constant is nothing but that is represented in terms of mu, and that is actually nothing but that is the viscosity. As we have not defined that this viscosity will be independent of mass, you can say that this viscosity will be the dynamic viscosity that will be depending upon the mass of the fluid also. The unit of stress is nothing but that is Newton per meter square, whereas the unit of mu is to be determined. You can also say that the unit of du will be nothing but that will be the unit of velocity, whereas dy is the distance and hence its unit will be meter. Now writing down again the same equation, you can say that mu upon s, hence the unit of mu will be nothing but that will be equals to Newton second per meter square. So this will be the final standard unit for mu, Newton second per meter square. But if we want to write down this in terms of kg meter second, you can say that Newton is nothing but that is actually the force into, that is the unit of force, and that is nothing but that is the mass into acceleration. Mass unit is kg, whereas acceleration is kg meter per second square. So writing down this Newton in terms of kg meter second, you can say that the unit of mu will be kg meter by second square into second upon meter square. So that will be equals to nothing but that will be the kg per meter second. So you can say that 1 Newton second per meter square will be equals to 1 kg per meter second, and these is the standard unit for dynamic viscosity. Or we can also say that the dynamic viscosity unit is equals to 1 Pascal second. Okay, fine. But if we are talking about the CGS unit for the viscosity, you can say that the CGS unit for the viscosity will be equals to 1 gram per centimeter second. And if we are talking about 1 gram per centimeter second, that is actually written equals to another new unit that is known as poise. If we want to derive the relation between the CGS unit and the SI unit of the mu, you can say that 1 kg per meter second will be equals to 1000 gram upon meter is equals to 100 centimeter into second. So you can say that 100 gram per centimeter second will be equals to 1 kg per meter second, and hence you can say that 1 gram per centimeter second will be equals to 0.1 kg per meter second, and 1 gram per centimeter second is nothing but that is 1 poise. So this will be the relation between CGS unit and SI unit of the mu. Now moving to the next term that is also related to the viscosity, and that is known as kinematic viscosity. As we have already discussed while discussing about what is mechanics, we have discussed that mechanics are of two types, that is dynamic and kinematic. Kinematic viscosity is actually defined for the kinematic mechanics, and we also know that kinematic mechanics is independent of the basic reason of motion, that is force, or that is actually the mass. So making the viscosity independent of mass, you can say that divide the dynamic viscosity by the basic reason for mass is density. This will be the relation between the dynamic viscosity and the kinematic viscosity. Here nu is nothing but nu is the kinematic viscosity. Using this particular relation, we can also derive the unit for the kinematic viscosity, and the unit for the kinematic viscosity will be written as mu is kg per meter second, whereas rho is kg per meter cube. Writing down the unit of this particular nu will be equals to meter square per second. If we are talking about the SI unit is meter square per second, but the CGS unit for this nu will be equals to centimeter square per second. And that particular centimeter square per second, we can also derive the relation between the CGS unit and SI unit. 1 meter square per second can be written as 100 centimeter square per second. So you can see that 10 raised to power 4 centimeter square per second will be equals to 1 meter square per second. And hence here is the relationship between the CGS unit and the SI unit of those two of the kinematic viscosity. Now we can also define here a new particular unit for the kinematic viscosity, that is 1 strokes, and 1 strokes is actually equals to 1 CGS unit of the kinematic viscosity, that is 1 centimeter square per second. That means again you can say that 10 raised to power 4 strokes will be equals to 1 meter square per second. This is again a new relationship for us to remember. Now moving ahead to the next particular part of the viscosity, that is actually the factors that affect viscosity. So moving to the first factor that affects viscosity is the temperature. Effect of temperature. If in liquids the temperature is increased, we also know that the value of cohesion will decrease, and as the cohesion will decrease, you can say that mu of the liquids will also decrease. But if temperature increases, there is another effect on the fluids, that is the decrease in density of the liquids. But the decrease in the density is very small, whereas the decrease in cohesion is more as compared to the decrease in the density. You can say that the effect on nu, that is actually the mu upon rho, value of mu will decrease, but the value of rho will also decrease, but this decrease will be smaller, hence the overall change on this particular ratio will be the decrease. But of course, as the denominator is also decreasing, you can say that the decrease in nu will be lesser as compared to the decrease in mu. So you can say that the change in nu and the change in mu, among these two changes, change in nu will be less. Both will decrease with the increase in temperature. So as the temperature increases, both decreases, but the decrease in nu will be lesser than decrease in mu. Whereas in gases, you can say that there is no cohesion, and as temperature increases, you can say that the basic reason of viscosity in gases was collision, and as temperature increases, the rate of collision will also increase. So hence you can say that as collision is increasing, the value of mu will also increase. But as rho of gas will also decrease with the change in temperature, you can say that mu is actually increasing and rho is decreasing, so the overall effect on the nu will be the increasing effect. But as the denominator is also decreasing, the overall change on this ratio will be much more, as the change of mu is also increasing. So hence you can say that here the change in nu and the change in mu both will be increasing change, but the increase in nu will be more as compared to the increase in mu for the gases. So I hope all the concepts related to the viscosity are clear in this video, and in the next video we will try to solve some basic numericals based on the Newton's law of viscosity. So keep watching the videos and don't forget to subscribe the channel to get notifications of the new videos upload.